Swayam Prabha. Digital India. Educated India.
Well, good afternoon, everyone. So, we would like to continue the discussion of one-to-one function, whatever we are doing in the last class. So, in the last class, what we did, let me summarize once again that we have defined the one-to-one function, into function, and onto function, and after the definition, we came across some of the examples how to categorize some of the functions, whether they belong to the category of one-to-one, into, or onto function. So, it's whenever we are writing y is equal to f x, f is nothing but a map. Okay. So, what this map does, this map takes up a value belonging to the takes up any value of x belonging to the domain of D and operates on it and maps it in the domain of y. So, therefore, depending on the functional form this and the domain of x, this y is equal to f x presents a range of y in the domain of E. So, this range, whether this range is a subset of the domain of y, that is E, whether this range is equal to the set E R, the range is denoted by R, whether R is equal to the set E, or whether R is a subset of E. Depending on that, we can categorize the function whether it is onto or into. If it is equal, then we call this function as onto. If R is a subset of E, we call this function as into. If for any two values of for a particular value of x in the D domain, there exists a unique value of f or y in the E domain, then we call it is a one-to-one function. If there exists more than one values in the domain of x and we return the same value in the domain of y after doing the mapping by the function f, then the function f is not one-to-one function. So, we have already looked into couple of examples in the last class. We will look into some more examples in this class as well. Okay. So, the next example goes like this. We have a function y is equal to f x is equal to sin x, and the x in radian lying in the domain 0 to pi by 2. Therefore, the domain of x is D is the domain of x, and this belongs to a set 0 to pi by 2, and once we put the value of the maximum value and the minimum value of x in the function, that will give you the range of function f. So, for x is equal to 0, y is equal to sin 0, and that will be equal to 0. For x is equal to pi by 2, y is equal to sin pi by 2, and that will be equal to 1. So, therefore, the subset, therefore, the set R in the y domain is called range of y, and this range is a set lying between 0 and 1. Now, we have to check the function, f onto, into, or one-to-one depending on several situations. Number 1, if E is lying between 0 and pi by 2. Number 2, if E is lying between 1 and 1.57, and third is if E lying between 0 to pi, that is 3.14. For these three separate cases, we have to check whether this function f is onto, into, or 1 to 1. Now, we have already determined the value of the set R, and for different three cases we have to compare whether R is a subset of E or not. So, let us consider the first case, case 1, E is 0 to pi by 2, that is 0 to pi is 3.14 divided by 2 is 1.57, whether my subset R is from 0 to 1. So, clearly if we have an axis like this, let us say this is 0, this is 1.57. So, 1 must be somewhere here. So, the subset, this is the set R and this is the set E, and of course, this R is a set which is nothing but a subset of set E. So, therefore, R belongs to E and it is a subset of E, and we come to a conclusion that f is an into function. Although the sine function is a periodic function, but so therefore, it will repeat its value for different periods of pi, but since the domain of x is from 0 to pi by 2. So, therefore, it will be having unique value of it will be assuming unique value corresponding to every value of x in the domain D from 0 to 1.57. That is the domain of x 0 to 1.57. So, for every value in this domain 0 to 1.57, sin x will be having a unique value, it will not be having a periodic value. It will not be periodic, means after a particular value of x, it will be assuming the same value. That is not the case in this particular problem, because the domain of x is not from more than pi 3.14, it is from 0 to 1.57. So, within this range of 0 to 1.57, for every value of x, there will be existing a unique value of y. That is why the function f is 1 to 1 function. Next, we look into the part 2. In part 2, your E is basically 1.5 lying between 1 and 1.57, and range of y is basically from 0 to 1. Okay. So, we cannot say that E is a subset, because this portion, let us say 1 to 1.57, this is E, and from 0 to 1 this is R. So, we cannot say whether R is a subset of E or not. So, R is definitely not a subset of E. So, therefore, f is not an into function, neither it is an R is not equal to E. So, it is not an onto function, but it is 1 to 1 function. Still this relation holds, because for every value of x, there exists a particular value of y in R, y in E domain. So, f is 1 to 1 function. Next, we look into the third part of the problem. The third part says that E is from 0 to pi. The set E is from 0 to pi, means 0 to 3.14, and in this case the range is from 0 to 1, and of course 0 to 1 is a subset of E. So, therefore, R is a subset of E, and hence f is an onto function, an into function, and of course it is 1 to 1. This is an into function for this particular case, and it is as well as 1 to 1 function. Okay. Now, let us go to the next problem. The next problem is, again we consider a function y is equal to f x, and f x is an exponentially decay function e to the power minus x, and x belongs to the domain 0 to infinity. So, therefore, domain is not d is nothing but from 0 to infinity. Now, we have to check the whether f is onto, into, or 1 to 1 for the for the domain of E from 0 to 1. This is given. If that is the case, first step will be, let us find out what is the range of y. The range will be obtained by putting the value, maximum value and the maximum value and the minimum value of x in the expression. So, for x is equal to 0, y is equal to 1, for x is equal to infinity, y is equal to 0. So, therefore, the range is varying from 0 to 1, and in this particular case the R and E both are equal, these two sets are identical. So, therefore, we can say that f is an onto function in this problem. Okay. So, next example I can take from part 2 of this problem. In this part we have to do the same thing if the set E is defined as 0 to infinity. It is not 0 to 1 in the earlier case. So, if this is the case, then what is the range of this problem? The actual range of this problem is from 0 to 1. So, of course, 0 to 1 is a subset of 0 to infinity in the real space. So, therefore, R belongs to the set E. So, therefore, f is an into function. Okay. So, likewise we can depending on the problem we are dealing with, we can identify what is the definition or is the nature of the function, whether it is onto, into, or 1 to 1. In both the cases, in part 1 and part 2, for every value of x. So, f x is equal to e to the power minus x. For every value of x, there will be a unique value of y existing in the domain of x. So, therefore, the function f is 1 to 1 for both the cases. Okay. So, let us move to the next problem. So, in this case our y is equal to f of x, and this in this case it is e to the power minus x by x. So, there will be a non-singularity in this case, and the non-singularity is at x is equal to 0, and the domain of x is given as 0 to infinity. So, therefore, our our domain is basically from 0 to infinity. So, we can define our d is from 0 to infinity. Now, depending on the value of set y, we have to check the categorization of the function f. For case 1, E is a set 0 to 1. So, in this case, now let us find out for the range of what is the range of y. So, minimum the x belongs so minimum value of x is 0 and the maximum value of x is infinity. So, therefore, for x is equal to 0, y is e to the power minus 0, that is 1 divided by 0. So, it is infinity, and for x is equal to infinity, y equal to e to the power minus infinity divided by infinity. So, it will be very small number. So, it will be 0. So, range of y is a set lying between 0 to infinity. Now, our in this case R is from E is 0 to 1 and range is 0 to infinity. So, therefore, it is not so the set E is basically a subset of R, not the other way around. So, therefore, R is a bigger set, R is not a subset of E. So, therefore, it is not. So, function f is not an into function, neither it is an onto function, but y is equal to e to the power minus x by x. In the domain of x from 0 to infinity, it will be having a unique value for every value of x, y will be having a unique value. So, therefore, f is a 1 to 1 function. Now, in case 2, our E is 0 to infinity, and we have already proved that our range is also from 0 to infinity. So, in this case R is equal to exactly equal to E. So, therefore, f is an onto function, and of course, it is 1 to 1. Okay. Now, let us go to the another problem, the problem number 4 maybe. So, in this case y is equal to f of x, and it is e to the power minus x divided by 1 minus e to the power minus x. Now, x belongs to the domain of x is from 0 to infinity. So, therefore, you can identify the domain from 0 to infinity. Okay. So, in this case we have to find out what is the nature of function f, whether it is onto, into or 1 to 1 for different values of x and for different sets of in case 1, the set E is from 0 to 1. In case 2, the set is from 0 to infinity. Okay. Now, let us first find out let us take up the problem number 1. First, let us find out what is the range of x. For x is equal to 0, y is equal to, it is e to the power minus 1 divided by e to the power minus 0 divided by 1 minus e to the power 0. So, it will be 1. So, 1 sorry, in the denominator will be 0. So, it will be infinity. In another case, when x is equal to infinity, then y is equal to okay. In the case when x is equal to infinity, the y is equal to e to the power in minus infinity and 1 minus e to the power minus infinity. So, this will be 0, this will be 1 minus 0, so this will be 0. So, domain, so R is also from 0 to infinity. So, in case 1, R is a bigger set compared to E. So, therefore, R is not a subset of E. So, therefore, F is not an into function, it is neither an onto function, but it is one to one, because for every value of x there exists a particular, for every value of x there exists a unique value of y. Let us go through the second part. In this part, E is equal to 0 to infinity. So, therefore, and R is also 0 to infinity. So, in this particular case, E is equal to R, rather R is equal to E. So, therefore, F is an onto function, and of course, it is an one to one function, because whether it is onto or into, but for every value of x there exists a unique value of y. So, therefore, it is a one to one function as well. Next, we talk about a very important concept, that is the completeness of space and convergence of a sequence, and the basic definition of convergence, and let us try to understand what is meant by the convergence. So, that has something related to the completeness of space, and it will be giving us an idea what is the convergence. It gives an idea of convergence criteria of a sequence. Let us first talk about what is the definition of convergence. Let us talk about a sequence. Consider a sequence UK. It is a sequence of vector. So, UK is a sequence of vectors, and we talk these vectors, they converge to U star, that is in metric space, if the metric between U of kth element and U star tends to 0. If the metric between the kth element of the sequence and k is definitely a large number, kth element of the sequence and U star, then the metric between these two tends to 0, then we call this the sequence UK is converging to U star. Now, so what is the exact definition? To understand this concept, the exact definition is that UK, the sequence UK tends to U star, that is the element in the vector, if for every epsilon greater than 0, where epsilon is extremely small number, there exists an n which is very large, such that metric between U and UK should be less than equal to epsilon for all values of k greater than n, that is, if k tends to infinity, metric between U and UK should be tending to 0. So, that is the definition of actual convergence of a sequence UK. We call that this sequence is a converging sequence, for there exists a very large number of n for which the metric between the sequence uk and u star should be less than epsilon. Epsilon is extremely small number, but it is positive, extremely small positive number. This relationship, this metric holds for every value of k where k is very large, k is greater than n where n is very large. In other words, if n is very large and k is greater than n, then k tends to infinity, the metric between u star and uk tends to 0. Then we call this sequence uk as a converging sequence. This simply indicates that for very large number n means for the later stage of the sequence, the sequence will be tending to a particular element in the vector space, in the metric space, and that particular if that is the case, then this sequence is called a converging sequence. Next we define a Cauchy sequence. The Cauchy sequence, let us say uk, we call that sequence as a Cauchy sequence if uk is a Cauchy sequence if for each epsilon greater than 0 there exists m p such that the metric between um and up should be less than epsilon for m and p are much greater than n, where n is an arbitrary large number. Okay. So, what then this sequence is called a Cauchy sequence. So, what is the fundamentals behind this idea is that in this case we are talking about the sequence u1, u2, u3 like um, p, okay. So, this is a sequence. So, we try to find out metric between the two sequences, mth sequence and pth sequence, where m and p values are extremely high. So, in that case, for very large number, for if you have a sequence of functions at a very later on stages, the for a large value of n, the metric between the two sequences will be extremely small. That means, they will be less than epsilon. The epsilon is a large is a small positive value, and they will be converging to a particular value. They will be converging to a particular point if it is the u is a function, and they will be converging to a particular element in the space if u is a vector. So, therefore, if this relationship is true for every m and p, for every element um and up in the sequence, the sequence is termed as Cauchy sequence. So, that means, if for particular value of m and particular value of p, where m and p is greater than n, if the metric between the two is very small, that will not help to term the sequence as Cauchy sequence. For every value of m and p, where m and p both are large number, that means, for a very large number of n, that means, the elements in the later positioned sequence, they are for every value of m and p, the metric between the two will be extremely small. That means they will be converging at that point for very large number of n. Then the sequence is called a Cauchy sequence. Once we know the definition of Cauchy sequence, then we will be able to define the complete space X. Let us define the complete space X. The metric space X is a complete space in which all Cauchy sequence in X converges to points or elements in X. Now, they will be converging to points if we talk about functions. They will be converging to elements if we talk about vectors. So, we call that space a complete space if all the Cauchy sequence in that particular space X converges to points or elements in X, then only that particular sequence is qualified to be termed as a Cauchy sequence, and the space is called a complete space. Now, let us look into an example. In this example, we consider a sequence x n plus 1 is equal to 4 minus 1 over x n. Okay. So, suppose we have this sequence and let us try to generate this sequence, and to start with is let us assume x 0 is equal to 1. Okay. So, we generate the sequence. So, we put the value n equal to 0, 1, 2 like that. So, it will be x 1 will be nothing but 4 minus 1 over x 0. So, it will be 3, x 2 will be nothing but 4 minus 1 over x 1, x 1 is already we have found out it is 3, this is 4 minus 1 upon 3. So, it will be 3.67, then your x 3 is nothing but 4 minus 1 over x 2 is equal to 4 minus 1 over 3.67. So, this will be 3.73. Now, x 4 is 4 minus 1 over x 3 and this will be 4 minus 1 over 3.73. So, this will be 3.7319 and x 5 is 4 minus 1 over 3.7319 and this will be 3.732. So, the sequence, so from this calculation we can observe that the sequence, the metric between the two sequences, consecutive sequences, let us say 4 and 5, 3 and 4, 4 and 5, 5 and 6, the metric between them two means the distance between the two of them will be extremely small and it will be extremely small epsilon which is greater than 0. So, sequence is getting converged to the value 3.732. So, this is basically if we look into this equation, this particular value is nothing but the root of the quadratic equation x square minus 4x plus 1 for this particular problem. So, if you look into the root, one of the root is 2 plus root 3. So, it is 3.732. Okay, root 3 is 1.732, so plus 2, so it will be 3.732. So therefore, this particular sequence, that whatever we have developed for starting point x naught is equal to 1, it will be converging to a value 3.732. Therefore, this sequence is a converging sequence for large value of m and n. For large value, large m and n, the metric between xm and xn tends to epsilon, that is very small number, that means they tend to 0. Okay. So, therefore, the sequence we are talking about is a Cauchy sequence. Okay. So, now let us look into the problem number, example number 2, where in this example we are talking about a sequence which is not a Cauchy sequence. So, we consider the sequence u k x is equal to half plus 1 over pi tan inverse k x. Let us talk about this sequence where k is an integer and x is lying between minus infinity to plus infinity. Its domain is basically the real line. Okay. So, let us find out what is u1 x. u1 x is nothing but half plus 1 over pi tan inverse x, and u3 x is just put k is equal to 3. So, what is u1 minus 1? u1 minus 1 is half plus 1 over pi tan inverse minus 1. So, this will be 1 upon 4, and u1 for the value x is equal to 1, this will be half plus pi by 4. So, 1 by pi will be cancelling out. So, this will be by, so 1 by 2 plus 1 by 4 is equal to, so in this case it will be minus 1 by 4. So, 1 by 2 minus 1 by 4, it will be 1 by 4, and in this case 1 by 2 plus 1 by 4, it will be 3 by 4. Now, as k tends to infinity, for large value of k, as k tends to infinity, u k x is equal to 0. K tends to infinity means it will become 0 for x lying in between minus infinity to 0, and this value will be 1 for x lying between 0 to infinity. So, therefore, if we plot this sequence, if u is in this direction and x is in this direction, then we have minus infinity here, we have plus infinity here. So, from minus infinity to 0, the u k value is basically the x axis. So, from minus infinity to this plus infinity, this minus infinity, from minus infinity to 0, u is equal to 0. So, you will be having a value here, just superposing on the x axis. On the other hand, for x is equal to 0 to infinity, we have the value of u as 1 here. So, therefore, this sequence is not at all a converging sequence. It does not converge to a point in the space, rather than it assumes two different values. In one domain of the space, it is assuming a value 0, in another domain it assumes a value 1. So, it is not a converging sequence, though. So, the conclusion is that the sequence u k is not a converging sequence and the space comprising of this sequence is not a Cauchy sequence. converging sequence and the space comprising of this is not also a complete space. UK is not a converging sequence, it is not a Cauchy sequence, and the space where this sequence belongs to, that space is not a complete space. Okay. So, next, so we have more or less covered the different aspects of onto function, into function, one-to-one function, as well as the define the Cauchy sequence. We define the convergence of a sequence, we define the completeness of space, and how the Cauchy sequence will be connected to the completeness of a space, and how to calculate the whether how to determine whether the sequence is a converging, whether it is not converging, and how it is related to the completeness of the space. Next, we talk about some of the basic fundamentals of vectors. This will be very important as we go along with this course. The first definition, we will just rebrushing our idea. The first definition is called a functional. What is a functional? Functional is a map that assigns scalar value to a vector. That means, it is a map that assigns scalar to a vector or a function. So, that is called a functional. For example, T of u is equal to a to b u x dx. Okay. So, u x is a function, okay, between the limit x is equal to a and b, and t is basically a functional. T is a functional. This functional operates on u x within the limit a to b in this particular manner. It is in the form of integration. So, therefore, it result, what is the result? The result is a scalar. The result is basically a point, and that point is nothing but a scalar. So, a functional is a map that operates on a vector or a function and assigns it to a scalar. And what is that scalar? That scalar may be an element in the vector space, or it can be a point in a function space. Then we talk about an operator and a linear operator. We term that operator as a linear operator if it satisfies the following criteria. Operator is a linear operator if it obeys T alpha u 1 plus beta u 2 is equal to alpha T u 1. It is basically T alpha u 1, and alpha being a scalar, it will be coming out of the functional. So, in more generalized form, it should be T alpha u 1 plus T beta u 2, and both alpha and beta are arbitrary scalars. So, therefore, since they are scalar, they will not take part in the operation or the mapping of the functional, then they will be coming out of the functional. So, it will be alpha T of u 1 plus beta T of u 2. If this relationship is obeyed, then the operator T is called a linear operator, and T of u is equal to 0 if the function or vector is itself is a 0 vector. Once we define the linear operator, then we will be in a position to define the linear combination of vectors. This concept is very important as far as solution of set of algebraic equations or set of ordinary differential equations are solved. Those will be appearing quite often in any chemical engineering application. So, what is the let us consider n number of vectors in n dimensional real space u1, u2, u3 up to un, where each of u I belongs to n dimensional real space. Then we call this combination alpha 1 u1 plus alpha 2 u2 plus alpha 3 u3 plus alpha n un is called a linear combination of all ui's if alpha is are scalar. So, this gives the this expression gives a linear combination of all the vectors u1 to un, and each vector will be multiplied by a scalar, and if it is presented in a linear functional linear form, then this linear form is called a linear combination of all the vectors ui. Now, there is something called trivial linear combination. We call that combination as a trivial linear combination if all the alphas are 0, then we call that linear combination as a trivial combination. And what is non-trivial linear combination? Non-trivial linear combination is that combination where at least one alpha I is non-zero. Where at least one alpha is non-zero, and we will be getting into a non-trivial linear combination where at least one alpha is non-zero. Once we get this linear combination concept very clear, then we will be in a position to define independent set of vectors, dependent set of vectors, and dimension of space. What is independent set of vectors? Independent set of vectors, for example, if we consider the class of sequence of n number of vectors u1, u2 up to un, so that they belong to n dimensional real space, and consider the linear combination alpha 1 u1 plus alpha 2 u2 plus alpha 3 u3 plus alpha n un is equal to 0. If this relationship holds for all values of, if all alpha i's are 0 for the above equation to hold, then ui constitutes an independent set of vectors. That means, if we have an equation, if we have a linear combination of all n number of vectors as alpha 1 u 1 plus alpha 2 u 2 plus alpha up to alpha n u n, if that linear combination is equal to 0, to hold this relation good, you have to have all the alpha should be individually equal to 0, then this set of vectors is called independent set of vectors. In fact, this concept is absolutely important when we are solving the set of algebraic equations in any chemical engineering process. Probably in the chemical kinetics is one of the example. So, in that case, if you have 3 unknown and if you have 3 equations or equations or 3 vectors, then any fourth vector or fourth equation will be redundant. So, if the 3 unknowns are there, then there will be 3 equations should be minimum required to solve the system. So, independence of vector or independent or dependent set of vectors will be directly related to the redundancy of the solution, whether the solution is a unique solution, whether there is a multiple solution that is existing in your system. So, dependent vectors and independent vectors is definitely a very extremely important concept for the chemical engineers. Next, we talk about the dependent set of vectors. In this case, if at least one alpha I is non-zero, to hold the above equation, this is the equation, then u I constitutes a set of dependent vectors. So, again the dependent vector, independent vector, there is a they are related to the redundancy of the system and uniqueness of the problem. Okay. Next, we talk about the dimension of space. We will look into actual chemical engineering applications after defining all these concepts clearly. We call the dimension of space x. Suppose we consider a space x, and in this space in x we have n number of independent vectors they can be functions as well. So, either vectors or functions, but every n plus 1 vector or function is a dependent one, dependent set, then we call space x is n dimensional. So, therefore, if we have a 3-dimensional space, then we have 3 independent, we have to have a 3 independent vectors. Every other vector present in the space can be expressed as a linear combination of these 3 independent vectors. This simply means, so therefore, the dimension of the space is n. So, fourth vector n plus 1th vector, the fourth vector will be, since for a space, for a 3-dimensional space, the fourth vector can be expressed as a linear combination of the 3 independent vectors. So, if we have a 10 dimensional space, then the so 11th vector will be basically a linear combination of the 10 independent vectors. Suppose this will be having a typical application in case of chemical engineering application in case of chemical reaction system. Suppose we have a chemical reaction system having there are around 10 number of species involved. So, therefore, if we like to solve the composition of all the species after the reaction, then probably we will be writing 10 number of equations. Then 10 independent equations we must be having in order to solve this set of equations of 10 set of system of 10 unknowns. Any 11th equations that we may write for whatever overall mass balance of or whatever balance, the 11th equation will be a redundant one. So, you must be having total number of, so it has a direct relationship to the degree of freedom of the system. So, whatever the degree of freedom in your system, you must be maintaining that. So, if you have a 3 unknown system, you must be having 3 equations. So, correspondingly, the dimension of the space is very important, that directly dictates the number of equations you are going to handle, and if you would like to form any equation that will be characterizing the system beyond the dimension n, then you will be over specifying the system, or that reduction the equation becomes a redundant one. So, we will be in the next class, we will be looking into how to test whether a set of equations, set of vectors are dependent vectors or independent vectors, and how they are related to the chemical engineering systems, and what are the different characteristics of these vectors, whether they are orthogonal vectors, orthonormal vectors, and how they will simplify the whole route of the calculations procedure, and we will look into all these aspects in the next class. Thank you very much.